notice is that the big difference here is they don't give us a table of different sample values. They give us a table with a computer-generated printout of the information that we need. So in here, the USDA has a survey, and they want to find the average price of wheat in July and September. And they give us this printout. And they talk about the 99% confidence interval. So this is the only difference in this one compared to the other one, is this time we're not going to be doing any kind of picture because we notice that both of our samples are bigger than 30. So we're good to go. So we start out with our statement, and we say that we want to find a 99% confidence interval for the difference, you can say the true difference, the difference in the mean wheat price between July and September. And then we can define those variables. So I guess I would say the mu j is the mean wheat price in July, and mu s is the mean wheat price in September. I like that. We'll try that. We will use a 2-sample t confidence interval for, and Mara said let's try mu j minus mu s, so let's do that. We have a random sample of 90 for July and 45 for September. The populations of producers is likely more than 900. So, oops, both samples.
They count as independent random samples.
Oh, did they really?
Yeah.
Oh my goodness. Both samples independent. Thank you very much, Marilyn. I should have just looked up there, but I was kind of just doing the normal thing. Oh, that leads me to my next one. Since really died. Yeah, that's funny. Since both samples are greater than or equal to 30, the CLT applies, and both are approximately normal. Bless you. Then we do the math, and when we do this math, again, I'm going to write down the formula. We talked about doing July first, so we're going to have x bar j minus x bar s plus or minus t star, the square root of, and then it'd be s j squared, sorry, over nj plus s 2 over ns. And when we do this, they gave us this information, so if I write it down, I would have 2.95 minus 3.61. Again, I would probably, even in the notes, write it down as parentheses, even though you probably know that you're supposed to do that. Plus or minus 2.704. And so this kind of applies now because when I was talking about a little bit earlier, this t-square that I got, I have to look for degrees of freedom. How many degrees of freedom should I be using? 39.
Oh, because there's not a
The sample was 40, right? No.
45.
44? So the 44 would be the thing that I would need to use, but do they have a 44? So I want to use 44. 44. Why did I say 39? I don't know either. 44. So that was kind of dumb. Sorry. 44. So that's how you're getting the thing. If you use the table, they don't have a 44 in the table, so you would use 40. Okay, so you have to use a more restrictive one. We're going to use our calculators. As far as I can tell, every calculator has that TCDF thing or whatever, so you can use it. Going back to this formula, if I put in the standard deviations that they give me and the sample sizes, this is what it looks like. So my first one was 0.22 squared over my sample of 90, and then 0.19 squared over my sample of 45. When you figure this all out, you get an interval that goes from negative 0.759 to negative 0.561, which means that on average, the price in July was less than, of course, the price in September. So as we write this down and put it in the context, we are going to say we are 99% confident that the interval from negative 0.759 to negative 0.561 captures the true mean difference in price of wheat between July and September. This means that wheat is on average between 76 cents and 56 cents less in July than September. And if we would have done it the other way around, we would just say that it's more in September than it is in July. So again, it doesn't matter which way you do it, put it in the context. So our next two examples is the same kind of thing, but this time we're going to talk about it with doing the test instead of the confidence interval, one with data, one with not. So the same thing as in the past, we're going to see what's going on. When we take the differences, we're going to say that either the differences are more than a certain amount, less than a certain amount, or not equal to a certain amount. We have a alpha, which is a significance level. When we do our plan, we talk about the test we're going to do. This time we're going to do a t-test, a two-sample t-test instead of confidence interval. For the difference between the two means, we talk about the random data. We talk about the normalness, and hopefully the central limit theorem applies. We talk about the independence. That's where the population is 10 times our sample. Notice how this looks the same as in the past. So here, in the beginning, you'll see that we have the two sample means subtraction, and we also have the population mean subtraction. And what they're trying to show is what's the difference between those two things, and that's how we find our t-value. You actually have already done this. That's when we minus 0, because normally the status quo is that the difference in the means should be nothing. And so this yellow highlight is saying that, but they write it down in the formula. And then the stuff you recognize is that adjustment that we have after the t-score, and so that's what the square root is as well. Degrees of freedom. is determined by the smaller of the two. We already talked about this in our last example. So that's how you find your degrees of freedom. That's the same as before. Find your p-value. Works just like finding our p-value in the past. And then when you draw your conclusion, if your p-value is less than alpha, you reject. If it's not, you fail to reject. Put it in the context. Let's try one. So the first one is where they give us a computer printout. There's no data. So they talk about commercials for Bounty paper towels, the quicker picker-upper. And then we want to know, are they stronger? So a bunch of AP Stats students decided to find out, and they did a random sample of 30 Bounty paper towels and 30 generics. Good news, central limit theorem. And so we're going to find out what happens based on the results. So we state, first of all, what's happening. And to do that, we want the null hypothesis. And the null hypothesis is that the mean of Bounty minus the mean of the generic towels should be equal to 0. And we want to know if that's true. And so we ask ourselves, really, we want to know if the mean of Bounty minus the mean of the generics is greater than 0. Is the Bounty paper towel have a greater carrying capacity? That's what we want to know. And so you have to define both these things, of course. So you say mu b is the mean number of quarters held by Bounty towels. And then, of course, that means that the mu of the generic is the mean number of quarters held by generic towels. So everything pretty much works exactly the same as it has in the past, except we use a two-sample formula. It works the same as a confidence interval, except now it's a test. So very similar. After we do this, we talk about which tests we're going to use. And so we say that we are going to use, can I scroll down, is that all right? So we will do a two-sample t-test for mu of Bounty minus mu generic. And we've already defined those, so we're good to go. We have a SRS of 30 from each type of towel. So both samples are approximately normal according to the CLT. So in that one sentence, I defined both the randomness and the fact that they're both normal. Let's see. For independence, we could say there are at least 300 sheets of each type of towel, which is 10 times the sample size. So both, I don't know, I have an E, are independent. And then we, of course, do our math. So when we find our t-value in this case will be the x bar Bounty minus the x bar generic. And then we're going to subtract off, oh shoot, sorry, our mu of the Bounty minus the mu of the generic. And we're going to put that all over our standard deviation of the Bounty squared over the sample of the Bounty plus the standard deviation of the generic squared over the sample of the generic.